Welcome to qnawire.
So in this problem, we're given that a proton is projected into an electric field of a uniform electric field that is constantly pointing upwards. And so we know that the electric field has a value for every point in space, and it will point upwards with a constant magnitude. So everywhere within the projectiles, within the proton's trajectory, it will be influenced by an upwards electric field of constant magnitude. And if we look at the Coulomb force, we know that the force on a charge due to an electric field is just the charge times the electric field, which in this case will just be Q times E J hat. It's always pointing in the upwards direction. And if we use Newton's second law, we know that this is equal to the mass of the proton times the acceleration of the proton, which I'll label A sub E. And since we can neglect gravitational forces, we know that this is true. We can solve for the acceleration of the proton, which would be Q over m times the magnitude of the electric field in the j hat direction. So the proton is going to be constantly accelerating upwards with an acceleration of this. And so this is sort of analogous to the projectile motion, where instead of downwards acceleration, we have upwards acceleration. And so we can use the projectile motion equations, just in the case using a positive acceleration, 1/2 a sub e t squared. And in this case, we do have a negative downwards velocity, or negative y velocity, v sub 0 y, which would be minus v sub 0 times the sine of alpha, using this right triangle here, times t, plus we'll set our origin such that the initial y position is 0 and the initial x position is also 0. Likewise, for the x coordinate at any point in its trajectory, there's no x acceleration, so this first term would be 0. So we would just have v sub 0 times the cosine of alpha times t. That'll give you the x coordinate at any time in its trajectory. And so in order to find the maximum height of the projectile, I'm first going to sketch it. Even though that's saved for part C, it's easier to do it now. We know that with a constant acceleration upwards and an initial velocity, it will follow a parabolic path, so something similar to that, in which it will hit its maximum height, h max, here, and it'll reach back to its initial height at a distance d, horizontal distance d from where it started. H max will occur when the velocity, the dy dt, is equal to 0. So it changes from a negative velocity to a positive velocity. It's instantaneously at rest, and that's the lowest that it will get. That will be h max. This will have a value if we take the derivative of this equation, a sub e times t minus v sub 0 sine of alpha. We want to know when this is equal to 0. We add this on both sides. We get this new equation. We solve for t. We find that t is equal to v sub 0 sine alpha over a sub e. This is the time at which h max occurs. So if we plug this time in for the y coordinate, we'll find the height h max. So we'll get 1/2 a sub e, time we just found squared, v naught squared sine squared alpha over ae squared, minus the v sub 0 sine alpha times this quantity, which would be v sub 0 squared sine squared alpha over a sub e. If we do a quick simplification of the first term, we'll realize that 1 power of the a sub e cancels. So we will have this fraction. And this is positive 1/2 of a quantity minus the full quantity. So this will be negative 1/2 the quantity. So negative v sub 0 squared sine squared alpha over 2 a sub e. And this is h max. All right, so that's the first part done. So B, we want to know this distance d at which the projectile gets back to its original height. We can do a similar thing above. The time, we want to find the time at which y is equal to 0. So we want to know the time at which 1/2 a sub e t squared is equal to v sub 0 sine of alpha t. We want to know when this is equal to 0, essentially. And we know that t equals 0 is one solution, which is when the proton is here, but we're not interested in that. So we can divide both sides by t here. And we can solve for t in this equation. And we'll find that t is equal to 2 v sub 0 sine of alpha over a sub e. This is the time at which we get to d, and we want to know the range or the x coordinate at this time. So we're going to plug this time into the x equation. So x max, which is equal to d, is equal to, we plug this value for t into that equation, we get v sub 0 squared times 2 cosine of alpha sine of alpha over a sub e. And this term in the parentheses, this is trigonometric identity. This is the sine of 2 alpha over a sub e. And this is d. This is our expression for d. C, we wanted to sketch the trajectory. Well, it'll move in a parabolic fashion, moving upwards, and it'll reach the maximum height below the surface, or below its initial height, and it'll get back to its original height at a horizontal distance d, for which we just calculated. That's relatively simple. And D, the last part, we're given that the electric field has a constant magnitude of 500 newtons per coulomb. The initial velocity has a value of 4 times 10 to the 5th meters per second, and alpha is 30 degrees. I want to take these values, I want to plug them in for H max and D. H max we had was negative v sub 0 squared sine squared alpha over 2 a sub e. A sub e was q times e over m. We'll bring m up to the top. And d was equal to v sub 0 squared times the sine of 2 alpha over a sub e. Same thing. A sub e is q times e over m. And bring m to the numerator. And now you can just plug in values. And if you plug in each of the values, and if you know that the charge of the proton, Q, is equal to 1.602 times 10 to the negative 19 coulombs, roughly, and the mass of the proton is approximately equal to 1.673 times 10 to the minus 27 kilograms. Or you know the charge to mass ratio of the proton or electron, it'll be the same. Or no, it won't be the same. The charge to mass ratio of the proton, if you know that, whatever value that is, you can also sub that in, put that into the denominator, since this is Q over M. If you take this back to the denominator, you can do that as well. So there's a few ways to calculate this using a few different values, but when you plug them in, you should get that H max is approximately 0.4177 meters, and D is approximately 7.235 times 10 to the negative 6th meters. These are your two values. And these up here are the two expressions found using solutions similar to the projectile motion equations.